We will be going on to 4.4, which will be on non-homogeneous equations with undetermined coefficients, or the process of finding undetermined coefficients. Just a quick recap back here. 4.3 was the complex root case for the auxiliary equation, and we looked at that. So I went through all this stuff. What I didn't get to was, I think, this part. Just going back to the original question for the harmonic equation. So if you have the harmonic equation, you of course have plus or minus I as roots, alpha 0, beta 1. And so applying the process, the general solution is that, which of course we knew that. We already knew that sine and cosine were solutions, but this can put it in the general case. And then did number 16 as well. Here's your auxiliary equation, characteristic equation, and you get, of course, two complex roots in that case. And then you just identify, I mean, these are pretty straightforward stuff here. Identify what the alpha beta is and substitute into your general form. And then, of course, if you want to get particular solutions, you have to have initial conditions and all that. I put up a couple more that might be a little more complicated just from the solutions. So you can check that out on 24 and 26, going through those. And kind of look at more of the details. I like to work them out, but sometimes I just run out of time. So, okay, let's go on now to 4.4. That's what we are on the concept of undetermined coefficients. So let's take a look at that. So this is the second order case, right? So you have y double prime, and y prime, and now what we're doing now is we're looking at the non-homogeneous equations. So we're going to set this equal to a function of t. Or in other words, this is equal to a function of t. And this will just be one term. And I think I probably should start writing stuff down. I have all this here. So this is one term. And it's really they're special cases. These aren't like, this isn't exhaustive, nothing like that. But it definitely comes up enough to go through all of these. All right, so let's get to it then. So in this section, we analyze 3-ish, I'll say, more or less, types, because there's variations of each, of single term functions for f of t. That's one thing I don't think they say that explicitly in the book, but it basically is a single term and of different types. Basically, we're going to look at a polynomial, we'll look at e and sine and cosine. Leaving out a whole lot of other trig functions, and other functions, but those are the ones we're mostly going to look at here, which, in practice, probably comes up a lot in applications and stuff. So, all right, so and this is just defining a few things, for m equal to 0, 1, 2, etc. Those are the non-negative integers. Let me spell that out better. So m are basically whole numbers, right? I'll just call them whole right now. So the non-negative integers are the whole numbers. We're going to have f of t equal to c, t to the m, e to the rt. That's going to be one type. And this goes through a whole derivation of how they do this. Just going to highlight so we have our own little way of looking at it. there's a lot there, so I want to just do that. So f of t is that. Okay, or, oops, not of, or if, so, or if r equals 0, f of t equals just ct to the m. So those really kind of two cases there. And then we have this case. So also, if, so there's different values of m and r. You look for if r is a solution to the auxiliary equation, you'll see all the different cases. Okay, so also if the other case is f of t equal to ct to the m, e to the alpha t cosine beta t, or basically it's the sign, everything's the same except sign. So f of t equal to ct to the m, e to the alpha t, sine beta t. And this is beta non-zero. So we don't want, we want to have basically sine and cosine in there. If beta is 1, well, then you're getting basically, well, if there's no cosine, then it could be the top. So we're looking at those cases, and we'll go through those. So so basically they derive what the solution is. You just got to find the coefficients based on m, alpha, r, beta, etc. Okay, so we use the method, this is what it's called, of undetermined coefficients. The method of undetermined coefficients is this concept. So our goal is to find a particular solution to a y double prime plus by prime plus cy equal to f of t, where your f of t is basically restricted to those cases above. So what you get then is that. So where f of t equals ct to the m, though that's like your polynomial, e to the rt, or the other two cases, f of t equals ct to the m, e to the alpha t, cosine beta t, or f of t equals ct to the m, e to the alpha t, sine beta t. So I'll call these, this is case 1, and this will be 2a and say 2b. Well, I guess I'll label them as we go. So we'll look at 1 and then 2 on what it looks like. Different values of m and r will give us different types of solutions. So the first case, 1, might as well make it a nice circle, huh? Because I can. Okay, so 1, when you have a double prime plus by prime plus cy equal to c t to the m, e to the rt. Okay, we're basically we have m as before. You could say like m is an integer and greater than equal to 0, something like that, doesn't matter. So if you have that, then the solution is this, and this is what they derive. I'm not going to go through all those details. It's a lot. So the particular solution of t is equal to t to the s, which will be either 0, 1, or 2. I'll show you why. Of a sub m, so that's whatever the power is on m, t to the m, and then the lower degree. So this is your polynomial based off of t. Okay, and then that's e to the rt. And then you have different cases. And then we'll use I. So you have s is equal to 0 if r is not a root of the auxiliary equation. So basically, if you have this form here, there'll be a value sitting here for r. If it's 0, then of course that's gone, and you just have this, in which case this is gone. All right, so then it won't be a root, because if you set equals 0, it's not homogeneous. So it wouldn't be this case. Okay, but if it is a root, we'll see those examples. Then it either is or isn't. So it might be like like 2 if r is 2, but the auxiliary solution might have like plus or minus I as roots. Those are different cases. Okay, so then you have 2 more cases. So s is equal to 1 if r is a simple distinct root of auxiliary equation. If r is a simple, so it's just 1, like it's distinct. Root of the auxiliary equation. And then 3, s is equal to 2 if r is a double root, so repeated. So a double root of the auxiliary equation. All right, so that's case 1. Case 2 is this. So case 2 looks like this. You have the same, well, not the same, of course. You have left-hand side is the same, but not the right-hand side. So left-hand side is ay double prime plus by prime plus cy equal to, and this is when you get the cosine and sine. So there's 2 of these, we'll call it AB. C t to the m e to the alpha t cosine beta t, or you have c t to the m e to the alpha t sine beta t. And both cases beta non-zero, otherwise you don't have that case. Okay, so this is my A, and this was the B as above. The solution for that case looks like this. So the particular solution, t is equal to t to the s, just like before. And then all the rest is the same. So all of this is the same. So I'll just copy it just because. So you have that. But then you get e to the RT cosine beta t, and then you will say plus the other term, which would be t to the s, and then this is a whole different polynomial. Same degree though. B sub m t to the m plus etc. down to b1 t and then b naught. And then that's still e to the RT sine beta t. And then you have two other cases, and they kept the same numbering, so I will as well. You have s is equal to 0 if alpha plus beta I is not a root of the auxiliary equation. So remember, the auxiliary equation is set equal to 0. So you check that first. Five, s is equal to 1 if alpha plus beta I is a root of the auxiliary equation. Okay, so this is all, of course, right there. I mean, they highlight what to do, but I tried to condense it maybe a little bit so you can see what to do. And the key to really doing this section is keeping track of your M and your R when you solve, and then of course alpha beta. So keep track of that because that's part of your solution. I was going to write something here. So note that if f of t equals ct to the m, like just a polynomial, that's implying r is equal to 0. Okay, and then just a note, so this is how we solve it. Apparently chapter 6 gives a more careful justification of all this. They basically say we guessed on all this and it works, so we'll do it because the concept of methods of undetermined coefficients is prevalent. Like, it happens a lot more than just this, how you set things equal and find the coefficients. That's really why we're doing this one. Okay, so before I go, I'll do a bunch of examples as well, but let's go through this one together. So this is, does it apply to the, does this apply? All right, I gotta copy this. Since that thing's in there, I gotta paste this correctly. So I just gotta paste an image. Close enough. Kind of bothers me like that, but anyway. So normally this is definitely something we would work out together. So I didn't assign that. I assigned every other odd, but it's actually good to go through all 8 of those. Basically, does 1 through 8, can you apply this method? And so I already wrote it up, but we'll go through it anyway. So let's check it out. So in the first one, again, all the answers are there, so you can already see them. Maybe I should have blocked them out. I don't know. Could always block them out. So pretend you didn't see it. I don't know. Okay. So, first one, is that a solution? And I actually went too far there, didn't I? Okay. I went too far in all of them. Oh well, we'll just fix it. So what you do, I'll just tell you what you do basically. So you go through and look at it. So is the power on T a whole number? And of course, no, it's not. So this power's right here is not a whole number. So this can't work. That's why I have a no there. Okay, so that one, of course, can't work. We'll just erase all of them. Oh well. Second one, we're looking at that. That's exactly the form, right? I mean, t to the third, that's a whole number, cosine 4t. So then in this case, your r would be 0 for your e. Remember, r is the power of the e part. So where is it? There it is, right there. So it's this form. M is cool. R is 1. Or actually, that was cosine, right? So right here, your alpha is 0. So alpha can be 0, but your beta has to be non-zero. Okay. Okay, so that actually should be alpha. Alpha is 0. And the next two types is a yes. So 3 is sine x, and then e to the 4x. Well, you can write that just as e to the negative 4x. And then that's your alpha is negative 4. Next one, this one's not as obvious. So how do you write 3 to the t? Well, if you just write that as e to the ln 3t, then your r is ln 3. So it works out nicely, because that's just the power on there, and it works. So you can rearrange some of them, not always. 5's a no, because it's not a sine or cosine. This one, again, not as obvious, but if you factor, that's just 1. Okay, so that one works. This one is exactly the right form. And this one's not, doesn't have to do with the right-hand side, it has to do with the left-hand side. That t is not a constant. So it has to be the right form. These are all special cases. Okay, so let's go on to examples. I have 10, 14, 16, 18, 24. So probably not do every single one, but we'll work them out as I do, because I think that's the most helpful.